Okay guys, so welcome back again to our next video. So in this video series I'm going to start the shikimic pathway, mostly commonly known as shikimic pathway. So both these words are, you may find both these words in many textbooks, so it's just mean the same thing. So first of all you need to know is that this shikimic pathway produces specially phenolic compounds like this, like phenols, quinones, phenolic polymers. Likewise, these are the main compounds which forms from this particular pathway. So most of these compounds which are formed from our shikimic pathway are not available, like it's not possible in our human biology, right? Mostly you can see these metabolized in plants, not in humans. So that's why mostly uh, these products we need to consume, like our body can't produce it on its own, so we need to rely on plants, so we need to eat them and digest it into our human body. So that's the main thing you need to know about the shikimic pathway, which is that it's not available in your human body. So, and most common products which are forming from the shikimic pathways are like this phenylamine and tyrosine, so which we are going to talk about in the next few videos. So in this video I'm going to focus on the introduction and the shikimic acid. So we are going to talk about the biosynthesis of shikimic acid. So let me write on this. So I have just draw the structures because it takes a lot of time to draw in using this pen and in Microsoft. So biosynthesis of shikimic acid, right? Okay, so we are starting with two compounds which is we call as commonly known as PEP, and other one is a little bit a complex name, so you do not have to remember these names, but there are some special there are some names which are most commonly used, like as very important, so you need to remember those things. So this molecule over here we call as D-erythrophosphopy. Let me write D-erythrophosphopy. Okay, so in first step what happens is, so here you can see this is a alkene, the double one. So don't be mistaken, like this is a one mistake I have done so many times, which when I am in my lectures and when I'm learning, I take the notes, and then after some time when I look at it again, I would assume there's an oxygen over here. I misspelled, like there should be oxygen over here. No, there are no oxygens over here. So this is just a CH2 group over here, right? This is the structure. So this is not an oxygen. So some textbooks contain it like this, and some textbook it contain like the regular structure like this. So both are the same. There is no oxygen over here. This is a alkene, like this is a double bond over here, so there should be a CH2 over here. Okay, so first step what happens is, another thing I forgot to mention, this P represents a phosphate group, right? This P represents a phosphate group. So first step is what's going over here is the phosphate group is connected to our oxygen, so this phosphate group will break into here, and you can see there's a carbonyl group here, so this bond will go and attack to our carbonyl. Due to that, this carbonyl group will attack and somewhat H plus over here, like say H plus. So this is the first step what we are going through our mechanism from these two molecules. So then we have this particular molecule. So let me introduce you to the PAP component here. So here we have a PEP component, which is newly formed carbonyl group. From here you can see newly formed carbonyl group, and this is the carboxylic group. So this is just a single bond, right? I'm just coloring it to represent the PEP group. So here you have this CH3 group here. Okay, so this is the PEP part. So this is the newly formed bond between this carbon and this carbon. So now due to this attack, this carbonyl group or this double bond go to a proton, which forms a hydroxyl group. So basically this is an aldol condensation. I hope you know aldol condensations. Like if you have no idea about the aldol condensation, which I assume very rarely, because if you are in this particular stages like shikimic acid pathway, shikimic pathway, you should be able to you should be able to know about aldol condensation and Claisen reactions. These are normal things for you. So if for any chance if you have no idea, then I would put my link over here. I have discussed about the shikimic acid pathway and aldol condensation, so you can easily go there and refresh your memory. Okay, so now what happens in the second step is a bond breaking would happen over here. So let me see. So you can see this is a phosphate group. I had told you that the P represents a phosphate group and there's oxygen. So this bond will be broken, right? This bond will be broken, and there's a hydrogen over here. You can see there's a hydrogen over here. This hydrogen will be removed along with our NAD plus. So basically, you know what the role is the NAD plus. NAD plus is there to collect a hydrogen from a specific place. So in this case, this hydrogen will be removed along with our NAD plus. So this bond will be broken to form a new double bond over here. So now here we have our new molecule. So I have just drawn this little bit mistakenly. Don't get misled over here. So this is not connected, right? This oxygen is on. This oxygen only bonded to this carbon, right? This oxygen and this carbon is not bonded. So I have just that's why I have just put a line over here. So this is a CH2 group. This is a CH2 group. This has nothing to do with this oxygen. Okay, I hope you have that idea. So don't get mistaken from here. And now in the next step, what happens is another aldol condensation, right? Another aldol condensation takes place. What happens? Here you can see a alkene group. Here you have a carbonyl group. So this will go and attack here. Because of this attack, this oxygen carbon double bond will go and find a proton in our product sample. So here we have our final product from the aldol condensation, right? I hope you get understand of this. So here you have the carboxylic group, here you have the carboxylic group and the hydroxyl group, which is formed from this oxygen carbon double bond, right? The aldol condensation, basically aldol condensation. So there we have there's a carbon over here. So here this carbon over here. So this is our that carbon, and the bond between this carbon and this carbon is here, right? Okay, now this is not that much important molecule, but this is an important molecule. We call this molecule as 3-dehydro, because you can see two hydroxyl groups, quinic acid. Right, 3-dehydroquinic acid. So there are 3 hydroxyl groups. That's why we are putting a 3. Okay, so this is a little bit little important molecule. So I don't want you to memorize the name from these molecules, but if there's a particular molecule which is more essential and more important that you need to remember that particular molecule's name, then I would mention it alongside my videos. So these are not that much important molecules, but you need to have an idea about this pathway, right? If you have given these two components, you should be able to go through this pathway. So now we are in here. Okay, so then in the next step you can see H2O molecule. A water molecule will be removed, dehydration. So you know there's a hydrogen over here. There are hydrogens over here. So this OH alongside with hydrogen removes basically the dehydration. So you know the mechanism, so I won't mention it here. So in organic chemistry, the basic organic chemistry, right? So just the elimination reaction. So here, because of that leaving of this hydrogen H2O molecule, we have formed a double bond between these two carbons. So this is a very important molecule. So this is 3-dehydro shikimic acid. This is 3-hydro shikimic acid. So I have just put a wrong conclusion over here. The 3 doesn't represent the number of hydrogen OH groups, right? It's basically represent the position of carboxylic group. So you know the naming, right? It's basically, so I just made a mistake. So here we have 3 hydroshikimic acid. So this is pretty much important because if you remember the ganolic acid, which is coming from this molecule, so we are going to talk about in this same video. So in the next step we add the NADPH. You know what the NADPH is, right? So basically like the NADH. So NADPH is a molecule which can contribute, which can give a hydrogen to our specific molecule. So here you can see only position which hydrogen can bind into is this carbonyl group. So here you can see the carbonyl group is now a hydroxyl. So this is the most important molecule in this particular video, which is shikimic acid. Shikimic acid. This is shikimic acid. So these are very important, right? The shikimic acid, you need to know the structure. You need to know the structure and the name as well. So NADPH is the reagent which we are using. So not we are using, basically in the biological systems of the plants and bacteria cells. So these are the this is the reaction procedure. So there's a small thing I need to mention, like it's not a big thing, but just think to this molecule, the 3-hydroquinone acid, right? So you add NADPH. Now what would happen? So there's no double bond here, right? This just the same molecule like the shikimic acid, but there's no double bond over here, right? So that's basically the quinic acid. So you can imagine, right? So there's it's just the same molecule like shikimic acid. There's no double bond over here because we have not done the H2O removing part. So just to this molecule we are directly adding NADPH. So there's no double bond over here. Only this carbonyl group is converting into a hydroxyl group. So from that we can obtain this quinic acid. So I have told you that this is a little bit important. So these two molecules are pretty much important. These two molecules are pretty much important. So I'm going to move forward with this particular molecule right here. Just the same molecule like this one. So this is the same thing, right? Same this. So you can obtain 2 important molecules from this particular structure. First one is this protocalycic acid. So how we can obtain this? You can see that basically dehydrations. So we are removing H2O, right? Dehydration. So this is dehydrations along with oxidations. Sorry, not oxidations, enolizations. So from dehydration and enolization, you can see we can remove a hydroxyl group to obtain a double bond over here. Likewise, so you can obtain this particular molecule. So there are 3 double bonds. Here you can see 3 double bonds. One is they are at the very first, so one is okay, and the next one is coming from this dehydration. You can see this is a hydroxyl atom, another hydrogen is there, so you can remove both these together to form a new double bond. Another one is from the enolization. You can see here this OH can form a what we call it like resonance structures, right? So this can go over here to form this double bond, so enolization can happen. So from this we can obtain this phenolic compound, not phenolic compound, like phenolic compound, basically the aromatic compound. Okay, so this is the other one, the ganolic acid. So basically one of the most important molecules, like it's act as antioxidants in more industry wise, it's very important. So it's basically the same thing like this. So oxidation is basically happening over here, oxidation and enolization, right? So there's one double bond over here, so other one can be obtained from the enolization and oxidation. So I hope you get the idea of this particular shikimic pathway. So we are going to move, like there should be around 6 videos about the shikimic pathways and their derivations. So the first thing is how we can obtain the shikimic acid, which is more important. So we are going to move in next videos and other ones, so with from this shikimic acid. So I hope you get the idea. Let's meet on the next video.